This screencast will talk about a couple of algorithms that use the divide and conquer approach. This is one of the most well-known design strategies, and it's best, I think, discussed by looking at the next slide. So basically, divide and conquer algorithms work the following way. They'll take a problem of some given size, and they'll divide it, hence the name, divide and conquer. They'll divide it into pieces, most frequently 2 pieces, but sometimes there are some applications where it's more than 2. And then they'll solve each piece recursively, generally, and then they will combine them in some way to get a solution. So if you're familiar with merge sort, the divide step is quite simple. You just take the array or the list that you're trying to sort, break it into 2 equal halves, and then call merge sort on each piece. Then you can assume that each piece comes back sorted, and then the combined step is the merge. We're going to talk about quicksort next, and we'll see that as opposed to merge sort, quicksort does all its work in the divide step, and the combined step is actually nothing at all. So in quicksort, the divide step involves partitioning, which we talked about in a previous screencast. So again, if you recall how partitioning works, we need a pivot, and there are lots of different ways to select pivots. I won't talk about that right now. And basically then you do the partitioning, which takes the list and puts all the things that are less than or equal to P, the partitioning element, in the front of the list, and all the things that are bigger than or equal to P in the back of the list. And then you exchange the pivot with the last element that's in the front part of the list where the elements are less than or equal to P. So you end up with something that elements that are less than or equal to P, P, and elements that are bigger than or equal to P. And then you sort the 2 subarrays recursively. So you call quicksort again, and it does it over and over again. And so we'll illustrate this in the next slide. So here's a picture. Here's our list of entries. We'll let 8 be the pivot. We do the partitioning, and so we have 8 in somewhere near the middle, hopefully, and we'll have the elements less than 8 to the left in the front and greater than or equal to 8 in the back. Then quicksort will be called on this list. We'll have 6 be the partitioning element. It breaks the list into the elements less than or equal to 6 and bigger than or equal to 6 with 6 in the middle. And then this gets partitioned with 4, boom, etc. And then finally, when you're done, you'll notice that you do this in place. You do all the partitioning in place, and that's only the real work. And you get all the elements up through 8 in order in the list. And so then you go back up and you do the same thing to the right. Now, generally speaking, there are lots of implementation details here that I'm not going to talk about. The choice of the pivot is crucial for good performance because you want to split the array somewhere in the middle. The partitioning scheme, if you recall from the screencast, there's one directional scan and 2 directional scans, 2 different ways to do partitioning. And then another important detail is typically you don't want it on small arrays, say less than or equal to 15 or somewhere in the teens, you don't want to do the recursive calls on very small problems. So you just switch to something like insertion sort. So here's some code, pseudocode, and you can see it's quite simple. All we do is check the size of the list, make sure it's big enough, and here's where you might do something about the list being small and calling insertion sort. And then all you do is call partitioning routine, then quicksort on the front, and then quicksort on the back. The complexity analysis, the average case, it doesn't fit the usual paradigms. It's pretty easy to come up with the recurrence relation. You just look up here. Quicksort on n elements is basically going to be quicksort on the index, the partition minus left, plus quicksort on the right minus the partition index, and then the partitioning takes big O of n work. So unfortunately, this doesn't fit into any of this sort of standard recurrence relations that it's easy to see what the solution is. However, with just a little bit of work, it's easy to see two things. One is that the best case is splitting down the middle. That's going to basically perform just like merge sort and log n. The worst case, then it's going to be theta of n squared, right? Because you're only going to reduce the problem size by one each time because the pivot is going to end up at one of the ends. In the average case, if you use randomization or some other ways to get the partitioning element, basically then the performance is theta of n log n. And in fact, quicksort performs better than merge sort in many situations because it's an in-place sorting algorithm, as opposed to merge sort has to do a fair amount of copying and takes up additional space. So to get the improvements here, you have to have good pivot selection. So there are a number of different ways that people do it. You can just pick the pivot randomly, or you can do median of 3 partitioning or median of medians partitioning. It's pretty essential that you switch to insertion sort on small sets so you don't have a lot of recursion calls on very small subsets, and this helps to eliminate the recursion. Again, it's considered to be the method of choice for internal sorting of large files in most cases. The selection problem is another problem that shows the power of partitioning to give efficient algorithms. So what is a selection problem? Well, given some data set, the selection problem might be find the median of that data set, which would be the middle number in the data set. Another example would be to find the second largest number or the second smallest number in the data set. This is equivalent to a concept that you might be familiar with, finding the percentile of a data set. For example, the 90th percentile is the value that divides the data set between 90% of the values that are smaller and the 10% that are larger. So, for example, if we had 1,000 data points and we wanted the 90th percentile, what we'd want is the 900th largest value in the data set. So here's some examples. Here's the data set with 9 values, and if we want to find the median, which is the 5th number out of the 9, it turns out if you, for instance, sorted these, you'd see that the median number is 8. If you wanted the third smallest number, you'd see that it's be 4, and if you wanted the third largest number, it would be 10. So how can you find the ith largest number or the percentile? Well, one easy way is to sort it, which you can do in n log n, and then just read off the index that you want and find the number. But the question is, can we do better? And partitioning, just like we worked in Quicksort to provide a better way of sorting, quicker way of sorting, we can actually use the same idea here with the selection problem. So let's see how we can put partitioning to work. So for example, here's our same data set we were talking about before, and we want to find the median. How might we go about doing that? Well, we could partition around some number, again, chosen at random or a median of 3 or some other way that avoids degenerate situations. And if we do that with this data set, we'll get the partitioning where we have 2 numbers before the 4, and then the rest of the numbers that are bigger than or equal to 4 after it. Now, 4 is now the third number. That's going to be what's returned. The 3 is what's going to be returned by the partitioning algorithm. So what can we do? Well, where is the median going to be? We know the median has to be in the back part, right? Because these numbers are all smaller or less than or equal to these numbers, and there's only 3 of them, so we know they all have to come before the median. So then all we do is look in this set of numbers. So in other words, the 5th number has to be on the right, and where? what number in the right part of the list? Well, the second number. So you've eliminated 3 numbers. So what we're going to do now is we're going to look in the second, in the back part of the partitioning for the second number, or actually our algorithm will look for the index, the number in the index 4 of the original array. Again, by partitioning that list. So take a few minutes and pause the video and see if you can come up with what the actual algorithm would look like to solve the selection problem using partitioning. So just assume you've got a good partitioning method that will return the index of where the partition is in the array, and see what you can come up with. So here's some code for Quickselect pseudocode, and as you can see, the first step is to partition. So we're given an array from left to right. So again, we're going to do it in place, just like we did quicksort. And what we're going to do is we're going to assume that we're working in some, initially working in some array from 0 to n minus 1, and k is an integer from 1 to n. And what we're looking for is the kth smallest element. All right, and so again, what we're assuming is that when this gets called, we've determined that all the numbers, recursively, all the numbers to the left of left, in the front of this, are smaller, and all the numbers to the right of right are bigger. So in other words, as we do the recursive calls of Quickselect, we enforce this condition that we've basically been partitioning the elements in such a way that the array we're currently working on is in the middle. Okay, so now what happens? We do partition on left and right, and we get an index back. Okay, and that's the index that split the array into smaller and larger numbers. Then we check to see if s is equal to k minus 1. Now remember, k is the index that we're looking for. The value in that index is going to be the value we're looking for the kth smallest element. And so, because we're, of course, indexing our array from 0 to n minus 1, what we really want is the value that's in the kth minus first slot that divides the numbers so that smaller numbers are to the left of that and larger numbers are to the right of that. So if we get that, that means we found it. And so then we just return that value. Otherwise, if s is bigger than k minus 1, where are we going to look? Well, that means we've found, if we were looking for, say, for the 10th number, and s was 15, right, we know we've got too many small numbers. So what we're going to do is we're going to look in the front, okay, and so we'll look in A left up to s minus 1, and again, we're still looking for the same index because we're working in this in place in part of the original array. And otherwise, of course, we're going to look in the back. So take a couple minutes and make sure you understand how this works. You might even try to take a small example and work through it. So here's our small example. It's the same one we've been working on. So here's our data set. We're going to assume 4 is the partitioning element. So we go through and we do the partitioning, and we get our 4 here. It returns index 2, so that s is going to be 2. And so s is equal to 2, but k minus 1, k is equal to 5. We want the median, which is the 5th. So s is less than k minus 1. So what that means is we're going to need to look in the back. So now we're going to look in this portion. So now we partition around 8. And luckily what happens when we partition around 8 is we get that 8 is in the 4th slot. So we check, and indeed, s is in the 4th spot. And so s is equal to 4, k minus 1 is equal to 4, so the median must be 8. So what's the efficiency of Quickselect? Well, notice the only difference really between Quickselect and Quicksort is that we only have to look in one half instead of the two sides. So for the average case, we can more or less assume, and you can prove, that it's going to be equivalent to this. Namely, we just have the number of operations being the number of operations on half of it plus the partitioning work. And so we're going to get that that's theta. Then there's a worst case though, and that's when the partition comes out badly. And so we want to avoid that. And so just like with quicksort, we want to get a good choice of the pivot. So we use random pivot or a median of medians or a median of 3, and that leads to an algorithm with big theta and efficiency.